All right, time to talk about anhydride chemistry. All right, so what we're going to basically talk about is how do you transform an anhydride back to a carboxylic acid. And what you first have to do is activate that anhydride um, by using a little bit of an acid catalyst. The acid catalyst will protonate the anhydride via one of the carbonyl carbons. And what you basically will do is now have the water attack the activated carbon of that carboxylic acid. So you have the water with its lone pairs, doing the attack on the carbonyl carbon. The electrons go back to the oxygen. Now the positive charge resides on the nucleophilic water that's now installed on the carbon chain. And then what happens here is that we're going to do a little bit of a proton shuffle. So we deprotonate that molecule, using another water molecule. So the water molecule attacks the proton, the electrons go back to that oxygen. So we end up with the neutral intermediate here. And then that proton gets added onto the opposite carbonyl. So the carbonyl technically attacks the acid, producing water again. And now that this carbonyl is protonated, what ends up happening is that we have an elimination taking place. Now, the elimination starts with one of the hydroxyl oxygens on the opposite end of the molecule. The electrons come down to the carbon, and what that does, it breaks apart this carbon-oxygen bond, brings it all the way here to the adjacent carbon, the carbonyl carbon, creating a new double bond, and in the process, these electrons get kicked out over here. So you end up forming a carboxylic acid, along with a protonated carboxylic acid. And then the last step is simply the protonation of the carboxylic acid to give you your neutral carboxylic acid. So as long as the anhydride that you start the process with is symmetrical, you produce the same carboxylic acid by the end of the reaction. But if you have asymmetrical anhydrides, then you'll end up with two different carboxylic acids. Okay. The same thing can be done with base instead of acid. And under the basic conditions, right, like sodium hydroxide, you attack the carbonyl carbon, the electrons go back to the oxygen, and you end up with your oxide derivative. Now, from the point of view of oxide, a carboxylate is a good enough leaving group as is. So here we have the elimination step taking place. The electrons go from oxygen back to carbon. The electrons move over back here, and the double bond kind of basically rearranges so that you end up creating a carboxylate ultimately, as well as the carboxylic acid. So if your task is to fully get the carboxylic acid through and through, then you have to basically do one more thing here. You have to take your carboxylate and you have to expose it to acid in order to protonate it, right? So water is not good enough. It has to be a dilute acid for this to work out, of a strong acid like HCl. And then that protonation will give you carboxylic acid throughout. And just like in the previous example, if the anhydride is symmetrical, you will get the same carboxylic acid from these two events. If the anhydride is asymmetrical, you're going to end up with two different carboxylic acids by the end of the process. Okay, so if you follow the roadmap of reactivity, what you should see is that the anhydride molecules are going to be reactive enough to produce your esters. In essence, you work from top to bottom in this diagram. That's the way you want to look at it. So we could turn an anhydride into an ester under acidic conditions in a very similar way as before. We simply treat the acid catalyst with anhydride. The anhydride attacks the proton of the acid. The electrons go back to oxygen. And the activated anhydride is now attacked by the alcohol. So the alcohol attacks the carbonyl carbon, the electrons go back to oxygen, and you produce the following tetrahedral intermediate. So just like we saw with water, we're going to have a proton shuffle take place, where we remove the proton of the oxonium cation, producing the initial intermediate shown here. And then that formed acid that we have there dumps the proton on the carbonyl oxygen, right? So in essence, the carbonyl oxygen attacks the acid and produces the conjugate base, which is just the alcohol. But now we have another activated carbonyl. And now, because you have the three oxygens present on the same molecule, they will act in an elimination fashion, kicking out the carboxylic acid, right? So here, choosing this oxygen, the one that has a hydrogen attached to it, we do the attack onto the carbon to create a double bond. That, of course, breaks apart this carbon-oxygen bond, and then we have a little bit of a shuffle in which the set of electrons come over here to create a new double bond. The electrons here move over to the oxygen, and you create a carboxylic acid as well as a protonated ester. So the protonation of the ester, will happen with just another equivalent of alcohol, removing that proton, kicking away the electrons back to the molecule. And yes, this will be the ester, by the way. Okay, so what you're basically seeing there is that you're going to get out of that reaction an ester, but then you get an equivalent of carboxylic acid. So another way to kind of get to the same end result is to do this under basic conditions, which means that you will be using alkoxide instead of alcohol. And the alkoxide is a much better nucleophile, enough to attack the carbonyl carbon. So when you do that, you break that carbon-oxygen double bond, the electrons move over to the oxygen, and you get that tetrahedral intermediate. And right here, we go ahead and undergo the elimination due to having three oxygens, ready with a bunch of lone pairs. Specifically, the oxygen that does it is the oxide, the one that is in connection with the metal, right? So that comes back down, breaks apart this carbon-oxygen bond, which moves over here to create a new double bond, and then that initial double bond is broken to create a new lone pair on oxygen. So you end up making a sodium carboxylate here on the left side, and here on the right side you have your ester. So if you want to, at this point, being the case that you do have formed a carboxylate, if you wanted to end up with the same ester to maximize your process, you could actually alkylate the carboxylate, basically do an SN2 reaction on methyl chloride. And if you do that, right, the carboxylate will attack your methyl, chloride will take off, you'll produce sodium chloride as a byproduct, but you'll create the same ester. And of course, if this would have been ethyl, then you will use ethyl chloride, etc., right? The only restriction is that if you're to do this, you have to select good SN2 electrophiles, right? You don't want to go beyond a secondary alkyl halide for this reaction. All right, now that brings us up to amides, right? We could take the anhydride and produce amides. And it's kind of the same story as what we talked about with the carboxylic acids, namely that you will have to balance the pH. This will have to be done at roughly pH of 4, otherwise you will basically kill all of your nucleophile. Okay, so under that premise, right, the anhydride will get protonated, reforming your amine, and then that amine will attack the carbonyl carbon, kicking away the electrons back to oxygen. And in the process, you'll form this tetrahedral intermediate that now has an aminium, portion to it. So the proton shuffle will take place here. You will deprotonate the nitrogen, right? Attack that proton, take the electrons back to nitrogen, producing the neutral intermediate here. And then you will protonate the carbonyl carbon, the same way that we saw for the previous reactions. So you protonate the carbonyl oxygen, the electrons go back to nitrogen, forming the amine, but now you have an activated carbonyl. And here you have two oxygens, one nitrogen on the same carbon, so plenty of electron density to carry out the next process. And specifically what carries the elimination will be, once again, the hydroxyl moiety. So the electrons of that hydroxyl come back down, allowed to break that carbon-oxygen bond, reform a new double bond here on the left side of the molecule, and you basically kick away the original pi bond onto the oxygen exclusively, and you form a carboxylic acid on the left side of the molecule. you have a protonated amide on the right side, and then the deprotonation is simply amine coming around, removing the proton from the protonated amides, the electrons going back to the oxygen of the carbonyl, and that basically completes the process. That's what will get you to the amide. But just like the carboxylic acid, I would say that yes, okay, there's too many moving parts. You gotta get the pH just right. The conditions have to be, properly thought about before you do this. Otherwise, you'll get into trouble, right? So I still think if you're trying to make an amide, acyl chlorides is still the way to go. Okay, and then one last one that we should talk about, which is basically the conversion of an ester back to a carboxylic acid. This requires a little bit of heating, but it's nothing too drastic. Pretty much, you treat that ester with an acid catalyst in the presence of water, right? So you have your hydronium cation. That carbonyl oxygen gets protonated, producing again water in the process, but now you have a protonated ester. So your water molecule attacks the carbonyl carbon, which is now activated. The electrons go back to oxygen, and this produces a tetrahedral intermediate, which undergoes deprotonation, right? Basically, proton shuffle. The oxygen of water removes the proton, attacks the proton. Those electrons go back to the oxygen, giving you a neutral intermediate. But the protons of this acid are now reallocated so that they go onto one of the hydroxyl oxygens, the alcohol or ether oxygen moiety. So you attack the proton, the electrons go back to the oxygen to reform water. And now that the alcohol is protonated, you can basically have one of the hydroxyl oxygens reform the double bond and kick out the alcohol leaving group, which is definitely a good leaving group at this point. So you form an equivalent of alcohol in the process, as well as a protonated carboxylic acid. And the last step is simply deprotonation, right? You have another water molecule come in, attack the proton, the electrons go back to the oxo, and you have your carboxylic acid, and you have reformed your acid catalyst. All right. So much the same way as we saw with anhydrides, you can also get to the carboxylic acid from the ester if you do this under basic conditions as opposed to acidic conditions. And in this case, that would mean using sodium hydroxide. The hydroxide will attack the carbonyl carbon, kicking away the electrons to the oxo. And now you have that sodium oxide that's coordinated right there. The funny thing about this is that technically speaking, you don't exactly have a good leaving group in the molecule, but basically you're going to be trading an alkoxide, which you currently have, for another alkoxide. So it's kind of a neutral situation in which, yes, those electrons come back down to form the carbonyl carbon, and then this carbon-oxygen bond is broken entirely, forming an alkoxide. But like I said, this is technically the same of, you started with an alkoxide and you ended up with an alkoxide. So it's almost like a neutral scenario. But there's one more thing about this that kind of benefits the process, and that is that the moment the alkoxide is formed, you're also forming a carboxylic acid. And the carboxylic acid is very acidic compared to an alcohol, to the point that the next step is kind of what drives this thing forward, namely that the alkoxide is now going to attack that proton of the carboxylic acid, get protonated in the process, and generate carboxylate, sodium carboxylate in this case. So that step is definitely totally absolutely favored towards the product side, and kind of helps out the process. So obviously, if what you want to get is carboxylic acid at the end, you just have to protonate that by adding some HCl, aqueous workup, and that will fix the problem. Okay, and you might have thought that was the end of the story for esters, but there's one more thing that actually happens with them, and that is that you can actually change the alkoxy group to turn an ester into a different ester. We call this a transesterification. And so basically, you're going to have an alcohol alkoxide mixture that you kind of go with. And this could be a problem if you select your alcohol and your alkoxide, to be different things. If you do that, then you're going to end up with a mixture of things. But yes, basically, this whole protonation, deprotonation, can happen, and then you end up with different alkoxides that can give you different products. All right, but anyway, with that said, right, we could start with an alkoxy group, an ethoxy group specifically in this molecule, and be introducing a methoxy group as well, right? So then this will attack the carbonyl carbon. The electrons will go back to oxygen to form the tetrahedral intermediate. And then the elimination route, which is the oxide will come back down to reform the double bond, will simply kick out an alkoxide out of this. And once again, this is not a great leaving group, but just like in the previous example, we are trading alkoxide for another alkoxide. So it's kind of like a neutral case scenario. And then this allows you to form a new ester, right? The one we had before was an ethyl ester. This is now a methyl ester. And as long as you're doing this, in excess sodium alkoxide, then you will definitely ensure that this is the main product. The other thing that you could also do to ensure that this happens is to simply perform this reaction in addition to using sodium methoxide, to do it in methanol solvent, because the ethoxide that you produce will probably react with methanol to produce more methoxide. And so that way you can ensure that you end up generating that new thing. All right, and then this last reaction, which is not really an option, ester into amide, you will have to basically play with the pH. But I'm going to tell you right here, right now, even before we start the mechanism, this is probably like the dumbest reaction that you could possibly try to get yourself into. You're not going to get a really good yield from this thing. So it will be kind of dumb to try this. But assuming that you get some, this is the way the reaction will kind of take place. You will protonate the ester carbonyl oxygen. That activated ester will then react with the amine to attack the carbonyl carbon, kicking the electrons back to the oxonium oxygen, producing the intermediate here. You will then deprotonate the nitrogen NH with a second equivalent of amine, and you will dump the proton on a different partner, specifically the alkoxy group of the intermediate, right? So the alkoxy group will then get protonated, and once that alkoxy group gets protonated, it becomes a good leaving group. So that's where the hydroxyl oxygen, which now move up here, will allow its lone pair of electrons to come down here, form a double bond, and in doing so, will also break apart this carbon-oxygen bond to form your alcohol. So now that alcohol is lost, and you are left with protonated amides, right? Which then will require you to have a second equivalent of amine, remove that proton and kick the electrons back to the oxygen to generate the final neutral amide. Now, once again, this reaction is technically crap, so I wouldn't do it if I were you. But for the small amount of reagents that actually make this happen, this is the way it technically happens. All right, so with that, we've basically covered everything in regards to esters. And as you saw, there was plenty of stuff to talk about. In the next video, we're going to talk about the amide chemistry. And because it's very, low reactivity compared to everything else, we're going to have less reactions to talk about. So I'll catch you up on the next video on what to do with amides. Okay, see you then. Bye-bye.